Hey there, hello, Sindre here. Question: what is a Monte Carlo simulation? There's a lot of Monte Carlo simulation across the many different courses in this university that I work at, but I've never really seen anyone try to explain what exactly is a Monte Carlo simulation. I've seen a lot of applications, but very little actual explanation. Just what is it? So a good way to start probably would be to look at definition. However, if you try to look this up, starting by a place where you shouldn't look, Wikipedia, you will see that there is no consensus on how to define what a Monte Carlo simulation is. Now, I have looked at a very large sample of different definitions, and they basically go like this. Monte Carlo simulation is defined as whatever it is we are using Monte Carlo simulation to figure out within my discipline. So these definitions are, or they tend to be at least, very discipline specific. It is defined as whatever task you're trying to solve. And what task you're trying to solve varies naturally from discipline to discipline. So what you really get is you could have a definition for physicists, you have a different definition for people who are geologists, you have a different definition for people who are doing risk management, you have a different definition for people who are economists, and so on and so forth. So there really isn't any way here to give a proper definition here without trying to look at a specific discipline. There are many interesting disciplines out there, but I'm an economist. So I will take the perspective of economics and try to look at what exactly is Monte Carlo simulation. So let's do that. Since our definition of Monte Carlo simulation is defined in terms of what we use it for, it's probably a good idea to look at what exactly do we use it for. We're going to do that, but first I'm going to just give you the conclusion here. So I've looked at a large sample again of different applications of Monte Carlo simulation within the discipline of business economics, because that's what I do. I do business economics, and if you do that, you will notice that there are certain commonalities. So first of all, Monte Carlo simulation is used for numeric calculations. So Monte Carlo simulation is a subset of numeric calculations. There are conditions and characteristics that comes in there, but fundamentally we use Monte Carlo simulation to calculate something. That's our point of departure. In other type of simulations, that is not necessarily the case. So for instance, you could simulate a car driving. There's calculations behind the scene, but the output here is could be like a 3D model of a car driving around. That's a simulation, but it's not a Monte Carlo simulation. So point of departure, Monte Carlo simulation is a numeric calculation, calculating something. Doesn't matter what it is, there has to be something. There are certain conditions though. Not every single numeric calculation is a Monte Carlo simulation, obviously, because if it was, then you wouldn't need the term Monte Carlo. We just say, okay, it's a numeric calculation. So only a subset of the numeric calculations are considered Monte Carlo simulations. So what are these conditions? Well, let's talk about it. First of all, in a classic standard calculation, the numbers. Numbers that are being multiplied together, added together, subtracted, divided, so on and so forth. But there are numbers in there. In a Monte Carlo simulation, we need to take this calculation, which is called a deterministic calculation. We need to remove at least one of these numbers with a stochastic variable. So instead of it just being a number, such as 2 or hundreds, millions, or 42, we replace that constant, this number, with a number that is the result of a stochastic process. Now we should probably define here what we mean by stochastic variable, stochastic process, or a random variable. But that is a deeply philosophical question that I'm not capable of answering this early in the morning on a Monday, on the first day of the semester. We can talk forever about how exactly do you define randomness and stochastic. We're just going to skip that. You have a colloquial understanding of what that means, and that's going to be good enough here to understand what Monte Carlo simulation is. But imagine we have some kind of numeric calculation, and at least one of the numbers in there needs to be replaced by a random variable, stochastic variable. So that's one of the conditions. The second condition here is that Monte Carlo simulation is a calculation, but you don't do it once. You don't just calculate it once. You need to calculate it many times. Not once, not twice, not 3 times, many times. And the difference is that every time you rerun this calculation, in all likelihood, there's going to be a different number for the stochastic variable. So in one calculation, the stochastic variable is going to still be a specific number in each iteration, we call it. So in one iteration, maybe it's 100. Maybe the next iteration it is 97. In the next iteration, maybe it's 108. But every single time we run the calculation, we're probably going to have a different realization of this random variable. So in Monte Carlo simulation, you have at least one stochastic variable, and you rerun the calculations many times. So that leads us to what exactly is the output here of a Monte Carlo simulation. Well, the output here is going to be a histogram or probability density function. Because since you have different inputs here, the different realization of this random process, the final answer is going to vary slightly every single time you rerun the calculation. So if you take all these output numbers and then plot a histogram, then that histogram is essentially going to be like the whole output of the Monte Carlo simulation. So within business economics, the primary purpose of Monte Carlo simulation is to generate a histogram. Okay, statistical distribution, probability density function, to be more precise. So that is a Monte Carlo simulation. A bit wishy-washy. So we're gonna re-say what I just said, exactly the same thing, just with an example, and maybe then it will be a little bit more clear. So let's do that. Let's look at an example. Okay, so an example from business economics. I feel like the most business economics-y thing you could possibly do would be to calculate the net present value of some kind of investment or project. If you are business economics students, you obviously know what net present value or NPV is. If you don't know what that is, I have 2 videos, one where I briefly explain the theory, another one where I talk about how to do the calculation in Excel. You can look at that if you want more details, but it doesn't really matter. So example here is going to be net present value. So the equation of net present value is pretty straightforward here, as you can see. Is the discounted sum of all future cash flows, and you subtract the investment cost. So there's some kind of calculation here. So I have a very simple example here, which basically just goes like this. The investment cost is 2,500. So what we can imagine here that we are a company and we are undertaking a project or investment, and the investment cost upfront is 2,500. Maybe this is in thousands, so like 2.5 million for instance. So, but 2,500 is what I wrote in the example here. Then this project or investment will generate income to us, or cash flows. That will be income minus the cost. So let's say this project has a duration of 3 years. So after we do investment, we're going to earn a cash flow share of 1,100 in the first year, 1,210 in the second year, and 1,331 in the third year. So completely arbitrary numbers. So you can calculate the net present value here. You take the cash flow and divide by 1 plus the discount rate. If you don't know what discount rate is, look at my other video. To the power of the time period. And if you do that, you get here a net present value of 500. So this right here is a numeric calculation, and it is perfectly deterministic. Every single variable here is deterministic. Each variable is just one specific number. The investment cost is 2,500. The cash flow in year 1 is 1,100. These are just numbers. So it is a numeric calculation, it is deterministic, so this is not a Monte Carlo simulation. But you can change this slightly and turn it into a Monte Carlo simulation. So how can we do that? Well, what we need to do is to take at least one of these deterministic variables, such as cash flow 1, 2, and 3, or the investment cost, and we need to substitute it with a stochastic variable. And a stochastic variable needs to be defined, so it can't just be like any number. It needs to be random number or number drawn randomly from some kind of predefined statistical distribution. So we need to come up with some kind of probability density function and then like draw a random number from that. Now in praxis, you don't actually do this randomly. You're using what they call a pseudo-random number generator. But I'm gonna skip the details on that. I have other videos you can look at for more details on that. So for example here, I'm gonna replace the investment cost. So rather than having the deterministic variable that is equal to 2,500 representing the investment cost, I'm instead gonna say, well, the investment cost is some kind of random number from this beta distribution, which has the shape parameter alpha equal to 2, and this shape parameter beta equal to 10, and then the minimum value or the lowest possible value of this statistical distribution is going to be 2,000, and the highest possible number of this statistical distribution is going to be 3,500. So I'm going to have my investment cost be some kind of random number from this statistical distribution. So why did I choose the beta distribution here? Not really any reason. I know a lot about cost tolerance, so I just use my expert judgment here to pick this particular statistical distribution. There are better fitting distributions out there, but the beta distribution is conveniently available to us in Excel. So it's a decently good fit and really easy to implement in Excel. So convenience here was an aspect here in my decision. But again, this is just like a fictional example. It's not really any numbers behind this. So the beta distribution will look a little bit something like this. It's a very nice shape here. It is asymmetric. So a random number drawn from this statistical distribution is going to be the investment cost. So we can draw such a random number, and we could end up randomly with 2,344.112427. So this will be the realization of this pseudo-random number generator. So this right here now, this is a numeric calculation, and one of the variable is stochastic, and in this particular calculation we have a realization here of something. But this still isn't really a Monte Carlo simulation. In order for it to become a Monte Carlo simulation, we need to just redo this calculation many times, several times. So if I do this again, maybe I get a slightly different number, I do it again, I get a slightly different number, I do it again, I get a slightly different number, and I keep doing this again and again and again and again until I feel like content, until I feel satisfied. So if you are doing this in Excel, then usually people say, okay, 10,000 simulations is enough, because if you try to do more than that with worksheet functions in Excel, it's probably going to crash. But if you use VBA, you could probably easily do 100,000 iterations. So you do it many times, and then you have a Monte Carlo simulation. So this simple numeric calculation, we replaced one of the deterministic variables, in this case investment cost, with a stochastic variable, a random number from the beta distribution. Do it many times, and that is a Monte Carlo simulation. Now, in order to finish the Monte Carlo simulation, you need to take the output there, the net present value, and you calculate a histogram. So I've done that. This is a nice histogram. This is the final output of the Monte Carlo simulation. So that is essentially Monte Carlo simulation, like the big lines. So many details that we have skipped there. Most importantly, like how exactly do you generate this stochastic variable? Like how exactly did I get these numbers here? Well, I used a combination of two things. what I used was called the universality of the uniform. So what you do is that if you want to get the random number from a particular probability density function, well, you need to integrate that to get the cumulative distribution function. Then you take the inverse to get the quantile function. And then as an input to the quantile function, you take a pseudo-random number. So that is a number that is between 0 and 1, which here can be interpreted as a probability. And the pseudo-random generator is basically a perfectly deterministic algorithm. So a pseudo-random generator is not actually stochastic at all, it just pretends to be, it just looks like it is. There's an enormous amount of details you can go into there. I don't really have a good video on that. I have one video though that you can look at, which kind of talks a little bit more about this, but it deserves more details. A second really big question here is, okay, how exactly do you choose a statistical distribution to draw random numbers from? You need to, that's also a very good question. I don't have a good video on that. I will probably make one in the future, but that's a really big question. Another really big question here is, okay, what if you have more than just one stochastic variable? What if you have two? It's easy, you can have as many as you want, but what is complicated here is, what if these two variables interact with each other? What if there is some kind of relationship between them? What if they are correlated? What if they are correlated but not linearly? What if there's some kind of complex relationship here? And in my opinion, that is where things get very difficult. Generating random numbers, pseudo-random numbers, is pretty easy. It's pretty straightforward. I have a couple of videos on that, so you can take a look at. Selecting a statistical distribution, statistical distribution. As did I say, this is early on a Monday morning, 6 o'clock. I lost my train of thought. Yeah, like simulating numbers is pretty simple. Choosing a statistical distribution, that is, it is easy to just do it, to get a reasonable choice. But it is incredibly difficult if you think about it. Nassim Taleb, his book Black Swan, like the gist of the book is essentially that the whole 2008 financial crisis happened because economists used the wrong statistical distribution when they were doing risk management. They were using a normal distribution, and instead they should have used what has become called the Taleb distribution. A distribution that has a positive skew, it has fat tails or leptokurtosis, and it is like a slight positive mean. Skewness should be negative. So yeah, so it is actually really difficult here to make the right choice in terms of picking a statistical distribution, but it's very simple to just pick some. There are kind of two methods you can use to kind of guide your choice. You can, of course, you can use expert judgment, but if you have data, you can use a method of moments, or you can use maximum likelihood estimation to guide your choice. So again, there's a lot of details into that, which we're not going to cover in this video. So yeah, that's going to be it for me. That was just like the basics of Monte Carlo simulation. For more detailed discussion, look at the other videos, look at all the sources, look at the lecture note. As you probably noticed there on the slides there, there's 200 on the presentation slides there. There's 206 slides, and we looked at 3-4 of them. So yeah, that's it for me. I'm gonna drink coffee.